Alcohol is recognized by the International Agency for Research on Cancer as a Group 1 carcinogen, with clear causal links to cancers of the ori cavity, pharynx, larynx, esophagus, liver, colorectum, and female breast. The risk does not stem from ethanol as a simple solvent, but from its metabolic conversion into highly reactive intermediates that damage genomic DNA. In this presentation, we'll follow the biochemical pathway from ethanol ingestion to the DNA lesions that initiate carcinogenesis when left unrepaired. Alcohol contributes to roughly 740,000 new cancer cases each year, about 4% of all diagnoses worldwide. Importantly, the epidemiology shows a dose-response relationship with no safe threshold. Even fewer than 2 drinks per day account for more than 100,000 cases annually. The pattern of risk reflects both direct exposure in the upper aerodigestive tract and systemic effects on metabolically active organs, such as the liver, as well as hormonally responsive tissues like the breast. Ethanol acts primarily as a pro-carcinogen. Its solvent properties increase mucosal permeability and enhance uptake of other carcinogens, while also promoting oxidative stress and endocrine disruption. The key carcinogenic species, however, is acetaldehyde, the primary oxidative metabolite of ethanol. Acetaldehyde forms covalent adducts with DNA and proteins, disrupting replication and transcription, and is itself classified as a Group 1 carcinogen based on strong evidence of genotoxicity. Most ethanol is oxidized by alcohol dehydrogenase, with CYP2E1 and catalase contributing smaller fractions, all converging on acetaldehyde formation. Detoxification depends on aldehyde dehydrogenase converting acetaldehyde to acetate. When production outpaces detoxification due to high intake, enzyme induction, or ALDH polymorphisms, acetaldehyde accumulates and can enter the nucleus, where it directly interacts with DNA. OECD Test Guideline 495 identifies this DNA reactivity as a central event in its mutagenic mode of action. The primary DNA lesion formed is N2-ethylidene 2-deoxyguanosine, created when acetaldehyde binds to deoxyguanosine and blocks replicative polymerases. More severe damage arises from acetaldehyde's bifunctional reactivity, which generates interstrand crosslinks that physically tether the 2 DNA strands. These crosslinks prevent strand separation during replication and transcription and are among the most cytotoxic and mutagenic lesions known. Their formation and persistence are key events in alcohol-related carcinogenesis, as documented in IARC Monograph 96. Beyond direct adduct formation, ethanol metabolism induces oxidative stress, particularly through CYP2E1 activity. This generates reactive oxygen species that drive lipid peroxidation, producing mutagenic aldehydes such as malondialdehyde and 4-hydroxynonenal. These aldehydes form exocyclic DNA adducts that often cause G to T transversions in tumor suppressor genes like TP53. Acetaldehyde can also combine with malondialdehyde to form hybrid adducts that promote chronic inflammation and fibrogenesis, compounding tissue injury. To counter interstrand crosslinks, cells rely on the Fanconi anemia BRCA repair pathway, which coordinates lesion recognition, unhooking, translesion synthesis, and homologous recombination. Physiologically relevant ethanol concentrations, around 20 millimolars, activate this pathway, marked by FAN-D2 monoubiquitation and BRCA1 phosphorylation. This response reflects the cell's attempt to manage acetaldehyde-induced DNA damage, and its efficiency determines whether lesions are successfully repaired or become permanent mutations. Genetic variation strongly influences individual risk. The ADH1B2 allele, common in East Asian populations, accelerates ethanol oxidation and produces a rapid spike in acetaldehyde. In contrast, the ALDH22 allele encodes an inactive detoxifying enzyme, causing acetaldehyde levels to rise 10 to 20-fold. Individuals with ALDH2*2 often experience facial flushing and exhibit markedly higher cancer risk at lower alcohol intake. These polymorphisms demonstrate how identical ethanol exposure can yield very different internal doses of the ultimate carcinogen. Cells lacking BRCA1 or BRCA2 are particularly vulnerable to acetaldehyde. These proteins stabilize stalled replication forks that encounter DNA adducts, preventing them from degradation by nucleases like MRE11. Without functional BRCA proteins, acetaldehyde-induced fork stalling leads to fork collapse and double-strand breaks that cannot be accurately repaired. This synthetic lethality highlights how acetaldehyde disproportionately harms cells with pre-existing DNA repair defects, with important implications for alcohol-related cancer risk in hereditary BRCA mutation carriers. The liver illustrates how alcohol produces organ-specific damage through a sequence of injury stages. Early steatosis arises when acetaldehyde disrupts protein secretion and impairs mitochondrial function. Acetaldehyde also drives hepatic iron accumulation, which fuels Fenton chemistry and intensifies oxidative DNA damage while stabilizing DNA adducts. As injury progresses, acetaldehyde activates hepatic stellate cells and directly stimulates collagen production, promoting fibrosis. Zoned 3 hepatocytes, rich in CYP2E1, carry the highest adduct burden, explaining the perivenular pattern of alcohol-related liver injury and the dose-dependent rise in hepatocellular carcinoma risk. In breast tissue, alcohol promotes cancer development both systemically and locally. Systemically, ethanol increases circulating estrogen by altering aromatase activity and hepatic metabolism, driving proliferation of estrogen receptor-positive epithelial cells. Locally, breast tissue metabolizes ethanol via alcohol dehydrogenase, generating acetaldehyde in situ. This combination is particularly hazardous. Hormonally stimulated cells enter S phase more frequently, increasing the likelihood that acetaldehyde-induced replication-blocking adducts become permanent mutations. This synergy explains the linear dose-response relationship between alcohol intake and breast cancer risk. Despite common belief, the type of alcoholic beverage does not reduce carcinogenic risk. Large meta-analyses show no protective effect of red wine compared with other alcoholic drinks, and white wine consumption is associated with increased melanoma risk, especially in women. Although red wine contains polyphenols like resveratrol, these compounds do not counteract acetaldehyde's direct DNA reactivity at physiologically relevant levels. Ultimately, the carcinogenic consequences of ethanol metabolism outweigh any theoretical antioxidant benefits of minor beverage constituents. Stopping alcohol consumption rapidly interrupts key carcinogenic processes. Within days, acetaldehyde levels in saliva and the colon return to baseline, and intestinal barrier function improves, reducing inflammation driven by microbial translocation. Over months to years, biomarkers such as micronuclei frequency, chromosomal aberrations, and DNA adduct levels progressively decline. This pattern highlights that continued exposure is required to sustain genotoxic pressure, and that meaningful risk reduction begins soon after cessation, even though full normalization may take longer depending on prior cumulative intake. Evidence-based policies consistently reduce alcohol consumption and related cancer burden. Fiscal strategies, such as excise taxes and minimum unit pricing, lower intake in a dose-dependent manner, with the strongest effects in heavy drinkers. Restrictions on availability, including limits on outlet density, hours of sale, and minimum legal drinking agents, further reduce consumption and associated harms. Comprehensive advertising bans, particularly those protecting youth, decrease initiation and overall use. Economic analyses show substantial productivity losses from alcohol-attributable cancer mortality, reinforcing the public health value of regulatory action. In summary, ethanol metabolism produces acetaldehyde, which forms replication-blocking DNA adducts and interstrand crosslinks. The Fanconi anemia BRCA repair pathway provides essential repair capacity, but sustained exposure or genetic vulnerability can overwhelm this system. When repair fails, especially under hormonally stimulated conditions, oxidative stress, or inherited repair deficiencies, lesions become fixed mutations that drive clonal expansion. Consistent with IARC conclusions, no level of alcohol consumption is entirely risk-free, and meaningful risk reduction is achievable through lowering intake or complete cessation.